Start the recording. Okay, fine. So, a very good morning, one and all. Today we are going to start the chapter number 2. That is nothing but the frequency selective network. On the topic of your the first content, you can say the resonance circuitry, and in that we will see the series and the parallel circuit. Okay. So here by the what we can say name itself indicating the circuitry will be either in the series or the circuitry will be in the parallel. The connection you can say the series as well as the parallel, and the component which we are connecting in the form of either the series or the parallel. If the components are nothing but that passive elements, that is nothing but your the resistor, inductor and the capacitor that we are going to connect in series. Connectivity will be there, and if they are connecting all the components RLC, if you are connecting in the parallel mode, then that time that circuitry will be the parallel. Okay, but why we are referring this word resonance, that we will see today. So see here, what is mean by the resonance? Resonance is the condition in the RLC circuitry in which the capacitive and the reactive reactances are equal. That is nothing but, we know very well the reactance denoted by the X. Okay, already you have studied maybe in the poly and the first year the basic concept related to the networks. That is nothing but the reactances. Okay, so the reactances are denoted by the X elements, and there are two reactances. One is related to the capacitor, other is related to the inductor. The reactant which is representing the capacitor value, that is nothing but the capacitive reactance, and the inductor, that is nothing but the inductive reactances. Okay, so these reactances are equal. XL is equals to XC. Okay, what is the condition to whom we can say the circuitry is the resonance? When the value of the capacitor as well as the inductor reactances are equal. This is the one of the what we can say the condition to say the circuitry is resonant. Okay, and in that we can identify the role of the register will be the pure registers. Okay, okay, so that's why there the indication will be the R will be treated as a 0. Okay, so the second is nothing but why we are preferring this resonance circuitry, because the constructions relating to the filters in many of the applications are required. That's why we are preferring this resonance circuitry. In that the first condition is XL should be equals to XC. Okay, and the Z will be treated as, that is the impedance will be treated as your the register, because the register plays the role of your the pure register. Okay, so that will be equals to your the impedances. Z will be equals to R, XL will be equals to XC. Okay, so here come to the first circuitry, that is nothing but the series resonance. In that we know very well we are connecting all the RLCs in series. But again one more thing is important, that is nothing but the circuit should be the AC circuit. Why we are saying the circuit should be the AC circuit? Just because the AC analysis will go on, and sinusoidal supply will be there, and the voltage drop across the each component will be different, and the current will be start to flow in the closed circuitry. So here also you can observe easily in the series resonance circuitry, if the word resonance is coming, it means directly you can say that my XL is equals to XC ideal cases, and my Z impedance will be equals to your the register. Now come toward the circuitry. Here the representation of a resistor, here the representation of the inductor, and this is nothing but my capacitor. But how you can write in terms of your the reactances in the AC circuit, that is mentioned here. My voltage will be, that is Vs is the source voltage, that Vs will be equals to your the Vm, that is nothing but you can say the peak voltage, or you can say the maximum voltage peak voltage. Okay, at a particular angle, and the current will be start to flow here. Now come toward the this point, how we can represent my inductive reactance, that is nothing but the XL. And okay, that XL is equals to, okay, that XL will be equals to 1 by omega L, that you can write here, and the XC is equals to 1 by omega C. So totally depend. Okay, 1 by omega C. That is XC is equals to 1 by omega C, and here will be XL is equals to omega L. So likewise the J representation is nothing but the real and the imaginary part. Whenever you are going to continue the AC analysis, we are aware the circuit will be the combination of the real part as well as the imaginary part. If Z is the impedance, so Z will be equals to R plus JX, where the X will be treated as your the inductive reactance as well as the capacitive reactance. Okay, but the X will be equals to either the XL minus XC, or X will be equals to XC minus XL. totally depend upon which value you are getting, whether the inductor value is the larger, whether the capacitor value is larger, or whether the inductive reactance is larger or the capacitive reactance is larger. So totally depend upon that, and accordingly you can take the difference of the capacitor as well as the inductor. Okay, so that's why here the meaning of the x is nothing but that may be the inductor, that may be the capacitor. While you are going to simplify the numerical, that time if directly mentioned, then well and good. If not mentioned, you can assume by the what we can say the value given in the numerical, or you can assume directly either the inductive reactance or the capacitive reactances and their values. Okay, so here this is the series resonance circuitry is mentioned. So at the resonance, if we are saying the resonance is happening, so again, apart from that, XL is equals to XC and the Z is equals to R. So while we are simplifying the numerical, you need to quote one line that is mandatory at resonance. It's not a common circuitry, it's a resonant circuitry. Okay, we are applying few conditions are there. Okay, that's why while you are going to simplify the numerical, you should mention directly at a resonance, then you can start to simplify the numerical. So what is that at a resonance? The impedance consists only the resistance component, that is Z is equals to R is the first meaning. The value of the current will be the maximum since the total impedance is the minimum. Okay, I will be max, okay, when the Z is the mean. So during this whenever the resonance is occurring or whenever the resonance circuitry is there, so we remember Z will be the minimum, that is the impedance will be the minimum, because we are, and the current will be the maximum. I is equals to V by Z. We are aware from the basic formula, I is equals to V by Z. So they are inversely proportional to each other. If the current is the maximum, the impedance will be the minimum. Okay, the second thing, the voltage and the currents are in phase. Due to this reason only, my the R will be equals to, they are in phase. That's why that R register is a pure register. R the value of the R will be equals to 0. Okay, R is 0, that's why the XL is equals to XC. Okay, because if you go for the sinusoidal waveform, okay, continuous sinusoidal waveforms are there, that time you will be able to identify what we can say while you are going to draw the figure of the reactive powers, active powers. Okay, that time you will be able to find what is the angle between the components of the voltage and the current. You will be able to find the whether the voltage is lagging, whether the current is lagging. Okay, which things, whether the current or the voltages are lagging or the leading in the R, in the L, and then the C. So likewise the angle can be calculated. So here in this case, whenever the voltage and the currents are in phase, definitely the R will be the 0. Okay, and the second last is nothing but your the maximum power occur at the resonance is the power factor is unity. Obviously in the ideal cases, the power factor, that is nothing but the either the vi cos 5, and the cos 5 will be treated as 1, so definitely the power will be vi. Okay, if the voltage and the currents are in phase, if the R will be equals to 0, if the XL is equals to XC, definitely my power will be maximum in this condition. Okay, now come towards the next, that is nothing but how we can write the other parameters, that is nothing but the in the series resonance, how I can write my the total impedances by considering all the values. Which values? That is nothing but the R. Which values? That is nothing but j omega O. Which value? That is nothing but my capacitor value. Okay, so all these parameter I need to what you can say keep in mind, how I can consider my resistor, inductor, and the capacitor, and how they will be represented in the form of the impedance equation. So the Z is nothing but the notation of your the impedance denoted by the Z measured in ohm. Okay, so already we are aware Z is equals to R plus JX. And just now I have explained X will be either the XL minus XC or XL plus XC. So you can write here the plus or minus if you want to reduce the circuitry. So you can write here the plus or minus. Okay, fine. So here they are assumed that XL is greater than the XC. That's why they written here the Z total is equals to R plus J of X. X is equals to XL minus XC. X is equals to XL minus XC. Okay, now the again the Z total. So what we have done, the J is the common, take this J outside, and in the bracket XL minus X will be there. Okay, and the bracket will be closed. Now the condition is that, okay, if I'm treating this, what is my condition at a resonance? At a resonance, XL is equals to X will be there, and the impedance total, that is nothing but equals to R. Okay. And how I can find my the maximum current? The other condition, that is maximum current you can get with the help of I is equals to either the V by R, that R is treated here the Z by this condition. Okay, so here the source voltage will become as a maximum voltage, and here the R will either become the ZT, or you can say the Z, or the Z will be equals to R, vice versa. So how I can find why we are going for this resonance circuitry is one of the things I have mentioned already for the filtering. Okay, for the filtering purpose, or to get the strength out signals, or to get to remove the noises. This is the one of the reason. But the thing is that the major role is the frequency. While we are doing all these things, we are interested in the frequency, we are interested in the, what we can say, to calculate the amount of the frequency, or we are interested how I can select my frequency so that I can get the benefit of this resonance. Okay, so the resonant frequency is the frequency where the condition of a resonance occur, definitely, no doubt at all. And how we can find how we are interested in the resonance circuitry, how we can find that, how we can select that frequency at a resonance, that is this zero indication here, the resonance. Because if you write simply the omega, so that will be in the normal cases, but if the resonance is occurring, some notation should be there, and that notation is nothing but the symbolic representation of zero is here for the angular frequencies, for the frequencies. So this zero, f0 is nothing but the resonance frequency, omega 0 is nothing but resonance angular frequencies, right? So here f0 can be already the derivation is there. Right now I'm not taking this derivation directly, I am mentioning here the formula. So resonance frequency is in the series circuit, resonance frequency in the series circuit will be equals to 1 by 2 pi root of LC, 1 by 2 pi root of LC, whereas you are aware omega is equals to 2 pi f, omega is equals to 2 pi f. So here what will happen for the omega? 2 pi f, so 2 pi will be cut out, and this if you are going to substitute this value, so 2 pi will be cancelled out, so omega will be 1 by root of LC, and the omega angular velocity is measured in radians per second, and you are aware the frequency is measured in hertz. So now the second parameters that I will show you very soon, that a graph, if graph is there, okay, then that time uh, in the graph, from we are going to start from the zero, then the peak, then the decline form. Okay, so the zero, peak, and the decline, in that cases we are thinking about the half power frequencies. That half power frequency is the frequency when the magnitude of the output voltage or the current is decreases by the factor of 1 by root 2 from its maximum value. Okay, already we are aware how we can calculate the bandwidth. During that we are focusing on the particular what we can say, the frequency. You have studied in the EDC also how we can take the VRMS and the VM values. Okay, so on the top peak we are never considered from the few amount, that is 0.707. On that we are going to consider the actual sicknesses. Similar to that only, here the meaning is the same. We are interested in the magnitude of that output of the voltage as well as the current when they are going to decrease up to 1 by root 2. Okay, if you are going to calculate, you will be able to find how we are taking from the 0 to that particular thing. So in this way you can calculate the frequencies. Okay, and why we are saying the half, because we are taking the twice frequency, one at the beginning and one is at the end, initial and the final frequency. So that's why the half hour frame frequency will be available in the two cases. Okay, either here will be the f1 and the omega 1, here may be the f2 and the omega 2. Okay, f1, f2, omega 1, omega 2. Likewise you can find easily, that is the half power frequency ranges. How I can find in the bandwidth, BW is the bandwidth. Okay, bandwidth between that is nothing but the difference between the frequency ranges. Okay, so that is the definition, or you can say the range of the frequency, or the how we are going to select the ranges of the frequency is nothing but the bandwidth. In other case, we can say the bandwidth is nothing but the difference between. Am I audible? Yes, am I audible? So now just continue the next, that is nothing but the bandwidth denoted by the BW or the beta, you can say. Okay, and in that, that is the difference between the two half hours, that is F1, F2, or the omega 1 and omega 2. Or you can say the width of the response curve determined by the bandwidth. Obviously, that we have studied in the ADC and other parameter, even in the basic fundamentals of in the first year on the polytechnic. There is a curve, and in that curve, two frequency ranges are there. Middle will be treated as a resonant frequency, and the initial and the final frequencies are nothing but F1 and the F2. Okay, so you can say the width between the F1 and the F2 is nothing but the width of the response curve by determining the bandwidth. Okay, so here the difference between the two angular frequencies, that is measured in the radians per second. Okay, and in other way you can define that bandwidth is equals to the resistor divided by inductor. Radians per second is the unit. This is the curve. Okay, so here this curve representation, first I want to mention here, this is the maximum or the peak value. This is the characteristics between the frequency and the current, and this is the peak value. Okay, Vm divided by R, because I is equals to V by R by Ohm's law. I is equals to V by R, so V by R, this V is the what we can say the maximum voltage or the peak voltage. But here we are not going to select from this point just because of this curve. This is unwanted or unnecessary signals will be there. We are treating here the constant from throughout the peak. That's why we are considering this section. We are considering this current, or you can say the frequency ranges. So here will be the angular frequency of one initial or angular frequency of the final, and middle is treated as a resonant frequency. So this will be the width, bandwidth, or the width of this curve. Okay, so initial, final, and this resonance. So here maybe the F1, F2, and the F0. F0, F1, F2. And if you are going to write the bandwidth, bandwidth will be equals to F2 minus of F1, or in terms of the angular, that is a V2, omega 2 minus of omega 1. Okay, likewise. So here 1 by root 2 we are taking as a 0.707 of Vm by R. So this curve is important while you are going to draw the graph, the current versus the frequencies. Here again the second graph, that is a characteristics are shown here by the curve, that is a voltage response curve, that is nothing but the voltage versus the again the frequency range. Okay, or the frequency or angular frequency. Here same similarly, V is equals to IR form. Okay, by the Ohm's law, V is equals to IR. So I is here the maximum current you will get, or the peak current you will get here. So Im by R, this one. And we are going to calculate the frequency ranges from this point, that is 1 by root 2. You can take the Im by R. So omega 1, omega 0, omega 2. So here again the F1, F0, and the F2, the bandwidth will be the difference between the initial and the final, these two in the voltage curve. So second important parameter apart from the frequency, because in the frequency selective network or the resonance, we are interested in the various parameter not done at the one side. First is the frequency, that we are aware. We are interested in the XL and HCl reactances. We are interested in the impedances. We are also interested in the after the bandwidth, that is nothing but the quality factor. Okay, so note on these parameters which are useful in the resonance or which are required in the resonance, that is nothing but the frequencies, that is nothing but the bandwidth, impedances, the reactances, all these are required. So similarly, apart from that, there is additional parameter, that is nothing but quality factor, and represented by the notation of Q. Okay, so the ratio of the resonant frequency to the bandwidth is nothing but the quality factor. How we can find the signals is qualitative, or the we are getting the whatever the transmitted by the transmitter, the same signals are received by that one by the analysis. Okay, how we are how the signal strength is effective, how we are selected the frequency. So one of the parameter by which you can identify, that is nothing but my Q, and the Q is nothing but the angular frequency, or you can say the frequency divided by the bandwidth. Okay, or if you are going to write in terms of the inductor and the, so ratio will be of the frequency into the inductor divided by the R. Okay, so in short you can say it also shows the sharpness of the response curve. would be the measured. Obviously, sharpness, the what we can say, the signal strength, the purity, okay, whatever that is required for the transmitting to the receiving point. So we are interested in the quality factor also. So these are required while you are going to simplify the network. You need to take care while if you want to reduce the circuitry, or if you are going to build the any kind build the circuitry, or if you are making the project, that time you should take care for the frequencies, for the bandwidths, for the reactances, for the impedances, and even the quality factor. See here the curve. So see here the second curve, which is the quality factor versus the bandwidth, you can say, and here the representation of a various quality factor from the what you can say least, medium, and the greatest, or you can say the greatest. How we can select the amplitude, how we can select the amplitude versus the frequency of that signals. At that time, this curve is required and the useful, just like your the voltage and the current versus the frequency curve we have seen in the previous slides. So here also the quality factor versus the bandwidth curve is also useful, okay, while you are going to do the things related to the resonance. Okay, if you are thinking about, if you are calculating the what we can say the numericals on that, this curve is required, how much amount of the amplitude you are getting of a on a particular frequency ranges, how you are going to find out that the bandwidth of each curve, and whether your quality what we can say quality factor is least, medium, or the greatest, that you can identify by that values. Okay, so higher the value of the q, the smaller is the bandwidth, means they are vice versa, you can say. If larger the q, the smaller is the bandwidth, okay, and the higher selectivity, okay, and the higher selectivity. So in short, you can say, if the quality factor is good, then the selectivity is good. If the quality factor is a lower value of the q, then definitely the lower value of the selectivity will be there, but no doubt at all the bandwidth will be increased. So in short, the quality is totally depend upon the selectivity of the frequency ranges. So Q is depend upon the F, you can say, but the bandwidth will be inversely proportional. So here come to the next circuitry, that is nothing but the parallel resonance. In the parallel resonance, just I have explained that depending upon the connectivity is totally on that the name itself indicating either the series or the parallel. If there is a parallel, definitely my all the passive elements are connected parallelly. So here you can observe the R is connected parallel, L is connected, and the C are all together are connected parallelly along with your the source, and the current is going to start to flow here. So see here in the parallel circuitry, what is the difference in the series and the parallel? Maybe the question will raise, maybe asked in the main examination and in other. So what is the condition behind that? What is the parameters or changes? So we are interested in the impedances in the series resonance, whereas admittance in the parallel circuitry. So in short, Z is equals to 1 by Y, or Y is equal to 1 by Z. So they are inversely proportional to each other. So always be remember, whenever the series circuitry is there, impedance is important. Whenever the parallel circuitry is there, the admittance is important. Okay, so the circuitry or the resonance circuitry, whatever it is, but the thing is Z is equals to 1 by Y, or the Y is equals to 1 by Z. So if a number of admittances, definitely YT is nothing but total admittance is the Y1, Y2, Y3. Likewise, why we are taking here the three cases? Because one is related to R, one is related to L, one is related to the what we can say the capacitor. Okay, as all are connected parallel. So one is related to R, L, and the C, they are in parallel. So for the R, 1 by R, for the L, 1 by j omega L, and for the C, 1 by j minus we have taken. Why we have taken? Just because they are parallel connected. Okay, so minus j by j divided by omega c. So likewise, you can simplify 1 by R. So this j minus is in the. So see here, so 1 by R, and this denominator is become here minus of j of omega L, and this denominator is come up, so j omega c. Likewise, 1 by R will be common for j, you can take out the common, omega c minus 1 by omega c. This equation is too important while you are going to simplify the parallel resonance circuitry, and at that time you need to calculate the y, just like you are in the series, the z is important. Similarly, in the parallel resonance, the y is important. So y is equals to 1 by r plus j of omega c minus 1 by omega l. So in the resonance, whenever the resonances occur in the parallel resonance circuitry, at that time, just like your the xl is equals to xc, similarly omega c is equals to 1 by omega l. So likewise, resonance will be occurring in the parallel omega c divided by omega l. No, the next is nothing but in the parallel circuitry, the impedance consists only the conductance, just like your the R, Y is equals to G is treated as a conductance, whereas in the series circuitry, the resistor R, Z is equals to R, here will be Y is equals to G. The value of the current will be the minimum. In the previous case, that was the current was maximum in the series circuitry, but here the current is minimum, that is I is equals to V by Y, you can say. So the admittance, total admittance is minimum, the current is also minimum, you can say, because in the voltage and the currents they are in phase also. So here in the what you can say the parameter in the parallel circuitry, the parameter is nothing but again the angular frequency, that is omega 0 1 by root of LC measured in the radians per second. See the things how they are connected parallel. So we are interested in the angular frequency omega 1 and omega 2, similar to like your the frequency ranges f1 and f2. But the thing is that we should focus upon the how the circuitry is connected. So parallel is important, that is nothing but 1 by r, 1 by omega c, 1 by omega, likewise. Okay, so that is important. So these are the cases in the half power frequency ranges you can calculate. So similarly, the bandwidth and the quality factor in the parallel resonance circuitry is mentioned here. The bandwidth, that is W is equals to difference between the frequencies. That is nothing but the final frequency minus of initial frequency. Okay, final frequency of initial frequency. So here will be, instead of omega L by R was in the series resonance, here will be 1 by RC. Here will be 1 by RC. The bandwidth will be also equals to 1 by RC, either the 1 by RC, or you can say the what we can say f2 minus f1 or omega 2 minus omega 1. So depending upon the numerical which is given, accordingly you can use either this formula or this formula. Okay, 1 by RC you can use, or the omega 2 minus omega 1, here f2 minus f1, depend. Secondly, the quality factor in the parallel resonance circuitry is nothing but the frequency divided by the bandwidth, you can say, or the angular frequency divided by bandwidth, or other formula is related to the angular frequency into RC. Okay, the resistor and the capacitor along with the frequency. So in this way you can calculate the quality factor in the parallel resonance. So in this way I have tried to focus on the theoretical part of your the resonance circuitry, that is nothing but the series resonance as well as the parallel resonance. In many of the what we can say the paper, the question arises related to the comparison between the series resonance as well as the parallel resonance. So first, how you can compare. First is nothing but the circuitry, or you can say the definition will be the first. Note on the point, the comparison between the series and the parallel resonance. The first point will be the definition, the second point will be the circuit draw, the third point will be the condition at a resonance, that is in the form of XLXC, that is in the form of Z is equals to R, that is in the form of the current is maximum or the minimum in the both the cases, voltage is minimum or the maximum in the both the cases. Okay, so likewise minimum 6 points, minimum you need to write the 6 points related to the comparison between the series and the parallel resonance. Okay, so this was regarding the introductory part of your the second chapter, that is nothing but a frequency selective network. In that we have seen the resonance, that is a series resonance as well as the parallel resonance. So I'm going to end the meeting today for the session. This is sufficient. Thank you so much.